Thank you everyone for coming along. This is our TUCS Tech Talk for week 9. Our presenter this week has developed somewhat of a reputation for talking about both fractals and PS3s. And this semester we're exceedingly lucky to have him back because he's going to talk about neither of these and is instead going to be talking about how Hello World works. So please make Jonathan Adamczewski welcome.
Thank you very much. Yes, I figured I'd talk about Hello World, the most simple of programs. You can see and Hello World there upon the screen. It's a deceptive thing. It's so simple, but when you start scratching the surface to see just how much goes between writing this sort of thing and being able to run it, and actually what goes into running it, there's a heck of a lot to learn there. In preparing for this talk, I've learned a heck of a lot in the last few days, particularly. I'm going to be working from the assumption that there are a lot of things in here that people aren't going to be familiar with. So I'm going to try to keep it simple and straightforward, and if I talk too quickly or I leave out some details, feel free to stop me and ask questions of clarification. That's one of the things I'd like. The other side of it is there's a good chance there's people here who know more about aspects of this than I do. And so if I say something that's outright wrong, please interrupt me and correct me. I'd be very happy with that. If you know something related or something more about a point that I don't, please interrupt and fill in. That'd be great. So the starting question, I guess, with what's here is, okay, if this is a program I've written, it prints Hello World. There's a function there, put to the screen. I've written a function, or I've written a program, in fact, that writes Hello World to the screen. I'm going to ask you now, actually ask you non-rhetorically, what sort of things are needed to get from that kind of code on the screen to actually getting it running and spitting out output? A computer, yeah. Actually, I didn't think of that one. I need to go. All right, yes? What? You got a computer. What else? Operating system. Yep.
So assuming you have a functional computer, what do you need?
Yeah, what else do you need? Well, operating system's not necessarily implied here because we'll get to that. Compiler is a good one. You definitely... Sorry? This one won't be. A library? Sorry, what was that one?
You need a library anyway, even if it is static.
That's true, on this system for sure, yes.
And then you need a linker.
You'll need a linker, yes. Any other stages in the compilation process? There's compiler, yes. There's a linker. There's actually something that sits in between them. Sometimes an assembler with GCC, which we'll be using. There's definitely an assembler in between. Preprocessor, yes. Very good. You need a way of running the compiler and the linker, that's true. You also need a way of running the generated program, which, for example, if you were cross-compiling for a different system, you don't necessarily have until you move it across somewhere else. Not doing that here, though. Any other things?
You need a loader.
A loader, yes. And with that, I'll throw this one in. A dynamic linker as well goes in that mix. So we'll look through. Basically, we'll cover. My hope is to cover in some small depth all these things that have been mentioned. So we'll get a sense of how this all fits together. So there on the screen, there's Hello World. It's all as it should be. Double check that. So we can compile it. Using GCC, as I said, GCC being the GNU compiler collection, but in this case it'll compile our C program into an executable program. So if we go tell it that we want the output to be called Hello World, and we want to compile the file helloworld.c, nothing happens except we now have a program called Hello World, which, Hello World, works, yes. Thank you. I'll be here all week. Yep. So we'll look at, though, what actually goes on underneath that. what we can do is we can ask the compiler to tell us more about what it does. The GCC actually, when we type GCC on the command line, but it runs a number of other programs for us to make it nice and easy, which gets us from this starting source code to a finished executable. So we can see what those look like with the -v option. -v tells us the things that will run, and I will do some piping shenanigans so that we actually get to scroll through it without it all disappearing in a hurry. So there we go. It gives us all sorts of things that aren't quite so interesting for this bit. This is how the configuration line that was used when GCC was built. Not really interesting now. This one here's a bit more interesting. This is the C compiler. CC1 is the C compiler that actually takes the C code and turns it into, you see at the end of the line there, this output file, something.s, which is our assembly language source code. From there, so that's the command line for CC1. You look down, you can see it mentions a number of directories that are searched through. Particularly these are for the preprocessor. The preprocessor looks through these directories to find files that may be included. And you see that some of them don't actually exist on this system, and include lots of this kind of parent directory notation, which makes it excellent fun to try to work out where they're really pointing to. We work through those, so we've run if the compilers run, the next thing as we scroll through is this line here, the assembler, the GNU assembler, which takes the assembly file that's been generated, the source code, and spits out an object file, which we'll look at in a bit. So that then runs, and further down, amongst all this other noise, we have this big blob here, which is how the linker is invoked. Now, collect2 is a wrapper around the system linker, and all those arguments get passed and things get worked out. But again, we'll have a look at that as we go. What we can do, actually I'll bring that back up. One thing you may have noticed or may not have noticed is file names in this kind of form, this /tmp/ a bunch of characters and then an extension. Each stage, as it was invoked, each stage writes out a temporary file that exists just between the stages being run. So there's a source file, assembly source file created, which sits in the temporary directory on the system here, and then that's fed into the assembler, which spits out an object file, which sits in the temporary directory, which is then fed into the linker, which spits out the final executable, and then the mess is cleaned up. What we can do, we can actually ask GCC to keep those files around so we can take another look at them. And we can do that with the save temps option. And so before I do that, if we have a look in here, you'll see there's really just those two files at this point. If we run that with save temps and have a look, we've picked up some extra files. So we have a .i file, which is the fully pre-processed source file. We have a .s file, which is the assembly code, and we have an .o object file. It's been added to the mix. Now, if we just quickly look at our original source code, you see #include standardIO.h. It's where particularly the puts function prototype is defined. Now, strictly speaking, I don't think you need that line. You could take that line out, it'd compile with a warning, but it'd still work. C is cool like that. But by leaving it out, you actually don't give the compiler the best chance to help you get your program right. You can leave it out and leave the warnings, or you can put it in, and when you pass the wrong things to the function, the compiler says that doesn't match the prototype that's in the header, try again. So we leave it in there. So there's our program, our source code. What the preprocessor does, the preprocessor is like a giant copy and paste machine. It does nice, fast, efficient copy and pasting of files into other files. It just does text substitution and things like that. So when we say #include standardIO.h, it goes and finds a file called standardIO.h, it takes the contents of it and it mashes it into our file for us. And beyond that, it actually does it. I'll jump to the end here. It actually does it multiple times to the point where we end up with a rather large file. This is our pre-processed source file compared to, that was from bottom to top. 857 lines. So our 7-line program to start with has been turned into 857 lines of pre-processed stuff, of which we probably only need one of those extra lines. But this is how this works. Now, one of the things I find myself wondering from time to time is questions of, if I've asked it to include standard.io.h, where did that come from? Where on the hard disk is that stored? Now, if you happen to know a little bit about how Linux operating system files are laid out, you can have a look in /user/include, which will have a bunch of files, and you can try to pick it out from there, and oh, there it is. You can look at it and try to fish it out that way. You can look at the list of include paths that we saw before and try to work out which one of those it might be coming from. Or you can actually use you can ask the compiler to tell you what files it's included. So this -M option is a nice little trick to help you find what it is. And you can see, though, that standard.io.h includes a whole stack of other things too. It's not just that one extra file. It fishes all around from inside /user include, as well as files that are installed as part of the compiler itself, the compiler package. So that's, there we go. We've made it through pre-processing. I'll take a breath and ask if there's any questions at this point.
No, but I just want to point out that's a makefile syntax, which is really useful if you want to do dependency checking in your makefiles properly.
Yes, it is. Absolutely. Thank you for the hint. Yes. So the -M option is used in make rules to generate dependencies, particularly as you change your source files and your dependencies change, so it'll can help catch that sort of thing. It's very handy. Any other questions at this point? We'll keep going. All right, so after pre-processing, we get to the next bit, do it that way, being this file here, helloworld.s. This is our assembly language source code. I think it's all there. Yep. So what this is, this takes the program we wrote, takes the compiler has worked its way through the 850 lines of pre-processed source and boiled it down to something that looks, in practice, not too dissimilar from what we started with. You can see that we have various instructions, moves and subtractions, these things that move data between registers or move data between different memory locations, or we have a line here, call puts. This is where the puts function is actually called. When we're done, it returns. We can see the main label that refers to the main function that we defined in our C code. It's defined as a global function here. We have our hello world string. So the elements of our program are here. Even if you can't read assembly language, and this is the horrible AT&T syntax to boot, even if you can't read assembly language, you can start to look and see how the data, the code that has been written, is being transformed as a step into the next stage. And so this is ready for the assembler to turn it into object code. So, yes, I think that's all I want to say about that one. So we'll have a look at the object file that's created next. Now, it's probably worth pausing for a second and looking at the file sizes here. We start with a 113-byte helloworld.c, which then gets pre-processed into a 17-kilobyte helloworld.i, the pre-processed source, brought back down to 351 bytes for helloworld.s. So that file we just looked at, 350 bytes in there. You would expect, perhaps, that these long-winded mnemonics and operands for each of the instructions. Each of these lines should actually shrink down to be a lot smaller in terms of memory space or disk space than they are when they're written out longhand like text, like this in text. When it's compiled to machine code, it gets quite compact. What we see, though, is that the object file has actually gotten bigger again. So we need to look at that and see what actually is that object file. It's not just the assembled code, it's got other things too. So we'll use the file command to tell us what that file is. And so it tells us that it's an ELF 32-bit LSB relocatable, Intel 80386 version 1 CISV not stripped. What does that mean? ELF is the particularly interesting bit. It's the format of the file. It's an ELF relocatable file. ELF is, I think I can remember this right, executable and library format. It's a format defined to make it easier to use bits of programs and libraries that are compiled with different tools, and they can actually be brought together and used. It's a common compiling interchange format. It's relatively popular across a number of platforms. And it defines a number of headers and sort of meta information within the file that helps other programs to know what exactly it is contained within this thing. So we can use the readelf command, and we can ask it to show us the elf header of helloworld.o. And there we have it, which really is a lot of similar information to what file told us, which is good because they agree. You see there's the word relocatable, there's ELF32, Unix, System 5, TUCS complement, little endian, 80386. So these are the common terms, but it's describing what's been packaged up and contained inside this in this file. There's quite a bit more than that. The assembler has taken our small section of source code and broken it up into different sections as well. So we can have a look at the section details that are in there. There are 11 section headers, it says. And so we can see a list of them. Some of them are less interesting at the moment. Some of them are more. The main one, perhaps, is .text. The .text section is where the actual compiled program code sits. It's the program text. It's the program code. So that's in there. We find there's this one called row data, read-only data, where our hello world string has been packed in. There's a comment in there which actually tells us who compiled the object file, and there's a few other things in there that I'm not going to look at right now. But we can start to peek inside and see what extra information has been stored in there. And so we have we have the ELF header. We can actually see there's no program headers in there because it's not a program. We have symbols defined within there as well, and we can see, amongst other things, there are two symbols listed here in this symbol table. One of them being main, which is our main function. One of them being puts, being the puts function that gets called, and you'll see that under the index column here, there's this undefined. It's not defined in this file. So far, we've gone from compiling source code, which has assumed that there's going to be a puts function somewhere but hasn't found it defined. We've assembled it, which has assumed that there's going to be a puts function somewhere but hasn't found it defined. We've created this object file which still doesn't know where this puts thing comes from. So it's still sitting there as undefined. It's waiting for that to come along before it can be used. So the next step we take is to link it. I'll go back and look at the output here, the big linker command line. What the linker does is it takes the object file that's there, it takes other things as specified, and it whirls them all together. It does that resolving of names. So the things that aren't defined, it seeks to make sure are defined or are sufficiently defined. It doesn't actually completely solve the problem for us, which we'll see. So there's this big long command line. The only really interesting bits, relevant bits to what we're looking at here, is that there's an input.println linux.o file, which I can't even see amongst the noise there. There it is. So there's the object file that it's loading in, and there's this one here, basically this -lc tells it to link the object file with the C library. And the C library is where a whole bunch of things are defined, including puts. So, again, take a look at the listing. We see that we have hello world as a program there. And if we run file on that, we'll see that that's similar to what we saw before. Same architecture, surprise, surprise. Maybe the key difference is this across the line here, dynamically linked. So we've linked it, but we haven't quite linked it. What the link has done is basically ask the question, can we, at some later stage, solve this problem? Will puts exist at some time when we actually want to run the program? And the link has been satisfied that may well happen. So it's spat out a program that's dynamically linked, which means when it comes to run it, some extra work is going to have to be done to resolve the dynamic symbols, the puts particularly, to the call that's in the program. We can also, readelf works nicely on the program as well. So you'll see probably the significant thing, this one's an executable file, not a relocatable file. We can actually look at program headers, which are a separate thing in here. And amongst these, perhaps the main one of note is this interp line here. Means there is an interpreter. A program interpreter is required, and the system contains a file. Most Linux systems have a file with this name, this /lib/ld-linux.so.2, which is responsible for doing the necessary interpretation, doing the necessary runtime dynamic linking to connect the dots, as it were, and actually mean we can call our puts function and say hello world. So we have that. We have, we see, if we start looking at the sections now, we see that there have been some more sections added, quite a few more sections added. If we look at the symbols that are in there, we can see that there's quite a lot of stuff in there. There's a range of init and constructor and destructor and start and finish and quite a range of extra things that have been added in there. This is part of linking with the standard library. This is part of what happens when the linker connects the dots between what the operating system expects and what you as a C programmer rely upon. When you write a C program, you just say main, int main, and then start writing your program logic inside there. You have the assumption that somehow your program will start running at main. There are other things, though, that the C language guarantees will happen or won't happen, and there's extra code added in, linked in statically to fill that gap. Now, that all gets in the way a bit of what I was hoping to show. So what we'll do is we'll rewrite our hello world just a bit to shave off some of this extra stuff that we don't need. So we go, we still include our standard io.h. When a program starts running, when an elf file is executed, the entry point, the first place, the first label that's looked for, is actually called underscore start. Okay, we start getting into underscore land. So we go underscore start. That's where every program begins. You don't normally see that when you're writing C programs. You don't normally see that when you're writing other high-level stuff because there's extra glue that goes in between to fix that up for you. So if we just compile this, what we'll find is that there's lots of errors. Because the compiler still thinks we're being regular everyday C programmers and wanting to start from main. And if we go to the top of this array of errors, we'll see there's multiple definition of start. What the C compiler is doing is saying, this is a C program, we need to provide a start function for you, a start symbol, that will then call your main function. Now, we don't have a main function, we've got our own, so we've got to tell the compiler to not do that for us. And so we can do that with no start files. We can say, I'll start my own program, thank you very much, and that compiles. Excellent. Now, let's try running that. Hello world, segmentation fault. When you start taking responsibility for things yourself, you get to keep the pieces when it breaks. So we need to change a couple of things in here to make up for that. Now, one thing, when a program ends, it's not enough just to let it fall off the end of the program and return. We've actually got to say the program has exited and tell the kernel, the operating system kernel, that we're finished. We've got nothing more going on. And so the way we do that is not with a return here, but we do that, we can do that with a function called exit. Now that's not actually defined in header that I know of, and so what we do is we tell the compiler, in the same way that puts is defined as something that will be sorted out later, we can tell the compiler that this underscore exit function is something that will be resolved later. And so we can say extern, which means it's defined outside this translation unit, extern void underscore exit int. And so we tell the compiler that there is a function called underscore exit that takes an int parameter that will exist at some point in the future. And that should be enough to satisfy it. Oh, need to bump the version number. So we compile that, and we run that, and there we go. We're back where we started. And if we have it, we list it, it's smaller than it was before too. It's bigger than 7K, now it's down. We've cut it down. We've left out bits that aren't actually needed in there. The pre-processed source won't have changed much, only the little bit that we changed there. But the assembly source will have changed just a little bit. So you'll see that the label here is now start rather than main. You'll see that there's a call to the puts function, there's a call to the exit function. Again, you can see that connection between what was written and what's actually being generated here. Our object file, actually I didn't show you this before, you can actually you can disassemble the program text contained within the object file with the object dump program, which, if we do that, you can see the column of instructions there is very similar to, not completely identical to, but very similar to what was in our assembly source file. You will notice, perhaps, that where we had call puts and where there was call exit, we've got this noise instead. Now this is where we start getting to the point of the linker. The point of the linker is actually to start linking things to other things to make sure that the program can actually run and go where it needs to. And so we have these that are essentially placeholders that the linker will replace at some point in the process. So we have that, and now we can actually object dump our hello world program, not just the object file, and we see our start function, which is what we saw just a moment ago, but we'll notice that these offsets have been replaced with different negative numbers that go to slightly different places. And so we've got names that are in here. We have puts at PLT and underscore exit at PLT. We can scroll up and see that these are defined further up. And this is where we start getting into the dynamic linking side of things. We still haven't resolved the connection. The connection between our hello world program and the puts function, wherever it may come from, has not yet been resolved. What's been put in are these, you can call them 3 instruction stubs. They're jumping off points to the function. They're not yet the function we're looking for. They sit there, and at runtime, the connection is set up such that you can actually call the function once the program's been loaded. Yes, I'll start going into that. So, well, actually no. I will pause and ask if there's questions at this point. There's a fair chance there might be.
Or are you also confused that you have no idea what to say?
You follow me so far? If I've left you behind early on, feel free to rewind and we can go back over some stuff if that would be useful.
Can I just ask, what was the magic X at the top of the header?
The magic what? Sorry.
Magic and then a X at the top of the L.
Okay. Yes. Let's go. The magic, you see the magic there. Magic bytes, I'm not sure how many of these bytes are magic. There's 16 bytes there. To my knowledge, the first 4 bytes are especially magic, and the latter ones are possibly less so. I'm not sure where the jargon comes from, but in a lot of when it comes to identifying what type a particular file has, it's often referred to as you look at some magic bytes that will tell you. And so particular file types will always have certain bit or byte patterns in certain places. And so you can tell it's that type of file, or you can have a really good guess that it's that type of file by looking at those bytes and saying, haha, this has the right magic. This is the file type I think it is. Or, okay, I see these magic bytes, therefore I'll go and check, I can go and check and see what other things are. ELF headers, those first 4 bytes, if they're that, it's probably an ELF file of some sort. If they're not there, most things will just discard it as that's not ELF.
You should be able to run magic against the magic command against that ELF file, and it will tell you that it's an ELF. Do you have magic?
I don't have magic.
Oh.
The file program that I mentioned before actually has a magic file that sits somewhere on the system with a large bunch of definitions of magic for a wide range of file formats. All right. Any other questions at this point? Okay. We'll soldier on. Bring that back. In fact, our source code here, in which we can see the start function that we wrote in C that we've compiled, and then we've got these couple of extra stubs. These aren't the functions we're looking for. As I said, this isn't the puts function. This isn't the exit function. This other thing at the top isn't either of them either. You can just ignore that for now. What these are, what these are is something like that PLT. PLT stands for, I found after much awkward searching of the internet, Procedure Linkage Table. The Procedure Linkage Table contains these little stubs, these little fragments of code that help the program and the linker get from a function call to actually finding the location in memory. At the point that the program is loaded, what happens is when we get to call this function, you call, let's say we get to the call puts function. Okay, that doesn't get to call puts. What that gets to do is jump to this PLT entry up here, which then jumps to something else. There's another section within the ELF file called the Global Offsets Table, GOT. Within that, the dynamic linker, when the program loads, the dynamic linker puts addresses, I don't think the dynamic linker does it quite yet. there are addresses in that table that are then used, it's an extra level of indirection, to find the function in memory that's being looked for. But, and I was saying, we didn't find puts during compiling, we didn't find it during assembling, we didn't find it truly during linking, and you don't even find it when the program loads. This is very lazy resolution here. It's located, and the value is set in the global offset table when the function is first called. The global offset table actually contains an address in the dynamic linker. So the program runs, it gets to the point of calling puts, which then jumps to the PLT entry here, which then jumps to what it thinks is the address of the function, but the first time it's called, it's not. It jumps to the dynamic linker, which then does a quick sleight of hand, fixes things up and puts the right entry in the global offset table, and then sends it off to call the right function. And finally, we get to actually write hello world. This special moment we've been hanging out for. So we have these many levels of indirection to give a great deal of flexibility when it comes to actually handling the dynamic linking of the program. We don't associate a given executable file with a system library at any stage, really up until the point it's run, and it's not really connected until it's done lazily at that stage because to save time in terms of program startup. But it's left lazy into the very, very last minute. And the same thing will happen, again, a little further on with the exit function. Again, it'll jump into the linkage table, it'll look up the address in the global offset table, it'll jump to that, which is really the dynamic linker, and it'll go fix up the address, call the function, and the program will exit. So there we go. There's a bit of an overview of how that runs. It's also, I think we've got to the point of it, it's now compiled, and you can kind of see, hopefully, how it fits together end to end. The next question is, how do you actually run this? What is necessary to turn this from a bunch of ones and zeros on disk into something that runs and produces these two glorious words upon our screen? And I'll run through this as a concept just quickly, but you see that there are a number of important systems, and they all fit together in quite a complex fashion. So you type // in this directory there is a thing called hello world, and you press enter. And what that does is that tells the shell, the program that's running and listening to your key presses, bash in this case, it tells the shell to run the program with this name. And so within the bash program, and I want to do this, within the bash program you have a function, which I grabbed the source code to this stuff. You can look through and you can trace through this and see how it goes. It ends up calling a function called execute disk command. It goes and finds a command on a disk and it executes it. Now, to do that under Linux, what is needed to execute another command is to talk to the kernel through the use of what are called syscalls, system calls. So we have our library calls, which all run in our libraries and our program run in what's called user space. We have system calls where we have to go to the kernel, which is the arbitrator of resources, and ask it to do something special for us. So the first thing we have to do if we're going to start a new process is actually create a new process. And the way you do that is with a function called fork. You fork the process. So one program that's running becomes two almost identical programs that are running. You create a copy of the bash shell process that's running in memory, all its memory, all the things it has, create a second one of those. And that happens there's a function called make child. And then that comes back, and we end up in a function in in bash called shell execve. Now, execve is the system call that is responsible for turning one process into another. It says, replace this process with another one that is loaded from this particular file. So what execve does, it says to the kernel, here's a file name, load it up, give it these arguments. And what the kernel does, it says, okay, let's have a look at it. Do we recognize the file type? Yes, we do. That's an ELF file. I know how to deal with ELF files. I have an ELF binary loader. And so it pulls in the ELF binary loader and says, here, load this. And the ELF binary loader looks at it and says, okay, what sort of ELF file is it? Is it one that needs is it dynamically linked? Yes, it is. Okay, we need the interpreter too. Where on disk is the interpreter? Let's load that. Let's load the binary file up, and we don't run the program, we run the interpreter first. So it takes the loaded binary file and gives it to the interpreter, which then goes and loads the necessary shared libraries. Getting there. From there, and you can find all this stuff. You can find all this stuff in the kernel source code. You can find it in the glibc source code. It's actually, I got to say, for me, it's been fascinating browsing through these source files. The dynamic loader function in ld.so is about 1,500 lines long. It's absolutely phenomenal. It's actually reasonably well commented. There's some interesting stuff in there. You can browse through it and learn quite a bit about how this stuff fits together. Likewise, the ELF loader in the kernel, in the Linux kernel, is reasonably well documented. It's quite structured code and not too difficult to follow. It's worth a look. Where did we get to? It's loaded, the interpreter's there, we've loaded the library, we've started the program. It calls puts and gets back to the dynamic loader to actually resolve the puts function for us. The puts function, once loaded into the global offset table, gets called. And so we end up in, let's go, because I think I know where this one is. Oh, I think I know where this one is. We end up in here. There's our puts function. What does puts do? Puts takes a string, it's passed a string, it writes it out, and it puts a new line character after it for us. So we didn't have to do that little \n. I could have used printf, but that would have taken a whole 4 extra characters to type. So we've got puts. Puts is a nice, simple, and it's also really simple to look at in this kind of way, whereas printf is crazy code. So what it does, it writes out, we get here, we've got this io sputn function, writes out the string, the length of the string, and then it calls this io put character, it writes out the \n, and it's written out to standard out, the standard output. This little function hides a stack of other function calls within glibc. They resolve to, in the end, a call to the write system call. At the end of the day, when you want to write something out, you're using a file in our Unix environment. It's written to a file, which means talking to the kernel to write it to a file. Even though it's showing up on the screen, it's still through a file descriptor. So we end up in a write system call. We go back to the kernel. The kernel does its write, which actually contains a whole other multiple levels of awesomely scary stuff, which I'm going to gloss right over, and then returns back to glibc. So we end up back, puts, finishes, returns to the program, hello world has appeared on the screen. The next call is to exit. Exit ends up, I'm not even going to try to find that one. Exit is a simple little assembly file which just calls the system call. It puts the return value in the right spot in the register, on the stack, whichever it is, both possibly, and then does the necessary interrupt to give control back to the kernel. And then the kernel cleans up the whole mess that we've done just to get these words show up on the screen. So this is hello world. It's simple. There's hardly anything to it, but I think it's been a fascinating thing for me to look in there and see how it all fits together. I think it's really useful to understand how these different parts fit together, how they relate to one another, to actually trace through. If you're running a distro like Ubuntu, it's really easy to install the necessary debug tools to be able to trace from your program into the standard library. You can't trace directly into the kernel because that goes into kernel space, which is a different problem. But you can see a lot about how you get from one place to another. You can actually trace into the dynamic loader and see what it's doing. All sorts of fancy stuff. So my hope is I've shown you some things that you may be able to use as you code. My hope is that you understand, hopefully, a little bit more, or maybe just a bit more familiar with some different terms. And I'd like to thank you very much for coming along.
Any questions for those of you who aren't completely confused? Josh.
Hi. Have you looked at trying to create the smallest Hello World program possible?
Smallest Hello World? No, I haven't. That would be an interesting project. I did see, in preparing for this, I did see a link to the smallest ELF program possible, which just returned the value of 42. If we look at if I do this quickly, we look at that header. That's a long form of the header, but it's a 50-something byte structure on disk. The smallest ELF program created was smaller than the mandatory header. It was 40-something bytes. It was a fantastic hack. Yeah, BusyBox has a lot of cool stuff like that, yes.
Because PUTS program is a .c file.
Sorry, the puts function was written in C, yes.
When is that? Does that have to be compiled?
It does have to be compiled. It's compiled to make the standard library, the libc library that sits on your hard. It's compiled by someone else, typically, unless you're a Gentoo user. So all that source code, and this is one of the cool things I think about Linux as a distro for learning this, or as a platform for learning this stuff. You have the source code. You can trace your way from Bash to the C library to the kernel. That's already all compiled, but you can get the source code and look at it. And when you install the things under Ubuntu, the debug packages for libc, you have the ability to run your program under GDB and just trace straight into puts and see where it takes you.
No other questions? Okay, please thank Jonathan for his talk.
Thank you.
I believe there's meant to be another talk in 2 weeks' time where we go considerably higher level than this, in that it will be on iPhone development, as far as I know, if we have presenters for it. But yes, that will be on the Friday, would be roughly the 12th-ish of 12th or 13th of May, I can't remember which. So see you all then.
Week 11?
Yes, the Friday of week 11.
We know what that means.
Yes. Probably more
So this
than
is,
dates.
if anyone wants to hang around and just see this, I'll do a quick run through the program under GDB, so you can see how you can trace through it. So the first thing being the call to puts. I need to tell it where to find the source code. And we can step into that. And so you see, if we go list, there's the put source code, which was briefly up on the screen earlier without the nice colouring. But we can you can step through that.
See all the calls that were made at any given time.
Yeah, you can actually step into some of those and get to all sorts of, which there are better ways to debug than command line GDB like this, but you get to see, you can actually see where things go. A lot of the way I work out how source code fits together is with grep or with a really cool little tool called ACK, which does a great job of finding, you say ACK, function name, and it'll search through files and tell you the ones that match. There are times when you're stuck with a virtual function call, like maybe in C++, or even some of this I/O stuff here in glibc. There's a virtual function table, a whole lot of indirects, and it's really hard to know where it jumps. So it's much easier just to jump into GDB, put a breakpoint in, and just you hit C to continue. So we can break, for example, at exit. Set a breakpoint at exit. Hit C to continue. We'll get hello world jump up on the screen because we've passed over that piece of code. We're now in the assembly source file where exit is defined, which it also tells me where on the hard disk that's defined too, so I can find it and change it or whatever if I really want to. Yes, and this is the thing, you have the source. You can do what you like. It's awesome. But you can see there we moves it into, from the stack into the register, and then calls the interrupt, which interrupt 128.